Yeah, so hey everyone, I'm Sid, and yeah, we'll be speaking about Lean-MLIR, which is, as we said, a tool for formally verifying Peephole optimizations. So yeah, let's begin. I guess, the first question one might ask is, hey, wait, what about alive, right? What's the relationship of what you do to alive? And good question for those of you who don't know what alive is. Okay, that's great. You're one of today's lucky 10,000. So let's consider these two programs called source and target. So source is a program that takes an input and then divides it by this number 8192, which is 2 to the 13. And then target's another program which takes a number and then shifts it right by 13, right? So if this were a Peephole optimization in a compiler, then we'd like to know that this optimization is correct. So if one feeds these two snippets to a tool called alive will then tell us, hey, the transformation seems to be correct, right? So essentially, this is what alive does. It takes source and target program snippets, and it checks that the semantics of the target program is equal to the semantics of the source program. Right. Now let's imagine that we maybe messed up the optimization, and we instead wrote an optimization that takes division by 1 and rewrites it to shifting by 13, right? This is an illegal transformation. So what does alive actually say in this scenario? So if you ask alive says, hey, look, the transformation doesn't verify, the values mismatch. And in particular, when the input value is 1, the source program returns the output of 1, and the target program returns an output of 0, right? So this is super useful, and in fact, it's so useful that if we sort of go look at the LLVM commit log, we just habitually see references to alive whenever somebody fixes an optimization or introduces a new optimization, right? This is part of the everyday workflow of folks who work on inst combine or these passes in general. Right, and there's a bunch of uses. So now there's a natural question of, okay, alive is amazing, but what about MLIR, right? Because alive's an LLVM-based tool. So maybe as a use case, let's look at Keizer, which is a compiler IR for homomorphic encryption. That's what the H and E stand for. So if we sort of go look at what IRs or what building blocks HEIR needs, one of the things it uses is a dialect called as the polynomial dialect, which represents elements in quotients of polynomial rings, whatever those are, right? It's some IR abstraction. Okay, so to be able to understand what makes it challenging to build something like alive for this dialect, let's maybe take a closer look at how alive works, right, and what it does under the hood. So more or less, here's what alive does. So we feed it the source and the target program. Now, what alive really does is it takes the source and target program, and it compiles it to a different IR called as SMT-lib. So more or less, SMT-lib is like an extremely tightly specified programming language, which only has sort of very basic primitive mathematical operations, right? So this is what alive does. Now, once it performs this translation, it then queries another tool called Z3. So Z3 is what's called as an SMT solver, and essentially one can ask Z3, hey, does the function called source equal the function called target for all inputs, right? So this is a question we can ask Z3. And Z3 is basically a genie, right? It's magic. I'm not going to get into how it works. But in this particular case, Z3 comes back and says, hey, the transformation doesn't verify, and it sort of explains why the values don't match. So sort of taking a step back, what alive really does is to find a good translation of LLVM into SMT-lib, a semantics preserving transformation, right? Which is not to say that this is easy or something. This is incredibly complicated because LLVM semantics are incredibly complicated, right? For those of you who remember the Poisson UB, it's been a journey basically, right? To even figure out the semantics of LLVM. So this is amazing work where they sort of nail it down. Okay, so we now sort of seem to have a general understanding of how alive works. So let's try to apply the same recipe for here, right? So we have this thing called polynomial dialect, and right now alive only works on LLVM, so the recipe seems fairly easy, right? We change the LLVM to MLIR, and right now we don't have an alive for MLIR, but it seems fairly natural to just ask the people who wrote alive, like Nuno and June and John to just write alive MLIR, right? I mean, it's easy, right? But the thing is, it's actually not easy, and essentially the reason it's not easy is because the objects that the polynomial dialect uses aren't easily described by SMT-lib. And so one needs to find either clever encodings of these mathematical objects into SMT-lib, but sort of more often than not, as the complexity of the IR increases, there's really no way to actually encode it into SMT-lib. So in some sense, these kinds of automated methods hit a barrier where there's no solver that can automatically solve for these things, right? So we instead pursue a line of research that, once again, the Alive folks themselves started, where they were thinking of re-implementing Alive inside a theorem prover called Lean, right? What's a theorem prover? We'll get to that in a bit. And so what we do is we essentially take their approach and we run with it, where we say, okay, cool, right? So we sort of implement a tool that lets us describe the semantics of MLIR dialects within a theorem prover and also provide automation whenever possible. So that's sort of our goal. Okay, but what is a theorem prover? So I'm going to go into a 3-minute detour into what a theorem prover is, right? So first of all, a theorem prover contains a programming language where you can define things. In this case, for example, I define a function called maximum, which does what you'd expect. Now, you can evaluate it, and it says max of 3, 4 is 4, as you'd expect. Now, the other thing that you can do in a theorem prover is to actually prove theorems, right? So you can say, hey, look, the maximum function is in fact commutative. Now, if I ask you to prove this on paper, you may come up with a proof like this, where you say, okay, I'm going to do case analysis on the values of a and b. If a is less than b, then something. If a equals b, then something. And if a greater than b, then something, right? Like the natural proof you might write down. So the cool thing about a theorem prover is that you can sort of take this English language proof and then sort of write it in a custom proof language. And the job of a theorem prover is to essentially check this proof that you've written down and to make sure that your proof is in fact correct, right? So Lean says yes, if and only if max is commutative. And your proof is in fact a valid one. So now if we sort of go back to the hair use case and we think about, we want to reason about this IR, right? So what do we do? Well, it's fairly straightforward if you have a theorem prover like Lean. Really what we do is we just encode the mathematical concepts that you need to talk about these things, which we possess in Lean. And then, if we want to sort of prove a rewrite, like x to the 2 to the n plus a equals a, which is legal because, for reasons, we just write the proof, right? I mean, because we're in a theorem prover. So sort of like stepping back, let's try to understand the sort of the space of these tools, right? So in some sense, we have on the one hand Z3, which is push button, right? It's like you just ask it a question and it presto tells you the answer, whether your transformation is legal or not. However, because it's sort of so automated, you eventually hit some kind of wall wherein you can't describe things. It's just too complex. On the other hand, Lean is on the bottom right, where it's super complete because you can really encode any mathematical concept you want in it. But really the issue is that you don't get as much automation, right? Now generally, whenever somebody plots a graph that has no scale or axis or whatever, the top right corner is where you want to be. And this is, of course, also the case in our graph, wherein we want to say that Lean-MLIR is in the top right, where we have a bunch of automation and we're also complete, right? But what does this really mean? Like, how do we achieve this? So really, the idea is that we use Lean as a language to describe the semantics of lots of dialects, and when you're dealing with a dialect like LLVM, which actually supports whose semantics are simple enough that it can be solved by an SMT solver, we make use of Lean's verified solvers to actually build these proofs. And in other cases, where we have dialects like the polynomial dialect, where the semantics are in fact too complicated for an SMT solver, we just encode the mathematics, right? So that's what we do. So in some sense, Lean-MLIR really lives in that green space that you see, where depending on the dialect that you have, and depending on how much automation Lean has for the dialect, it's going to be sort of either push button or manual, right? But really the goal is that you never get stuck when you're trying to reason about your dialect. So now that I've done a bunch of marketing, I'm going to hand it over to Alex to give you details, right? Yeah.
Well, thank you very much, Sid, for the sales pitch, and let's get down to the nitty-gritty. So the goals of MLIR, the first thing when we said to people that we want to formalize the semantics of MLIR, they said, you're crazy, MLIR doesn't have semantics. It's a collection of syntax. And that's kind of a problem. So we want to kind of build this framework as a way to start that discussion and to, well, actually build semantics and gain a shared understanding. And we're specifically focusing on people verification. And they're like sort of the green rectangle that Sid showed. We want to see where dialects could be easily verified. We want to make it trivial by building automation as much as we can. But we also want to really lean into the possibilities that Lean gives us. And even the harder dialects, which use complex mathematical objects, we're still able to express and we're still able to prove things about them given sufficient effort. So let's go broadly over the alive experience for MLIR. First, we'll show you some examples which specifically talk about LLVM optimizations, where we have built a lot of automation and it's kind of push button. Then we talk a bit about polynomial again, where we go into the complex mathematical objects involved, and finally we go for the framework and kind of how you could define your own dialect. So we start by defining, well, the sort of the left-hand side and the right-hand side, the two program snippets that we also give to Alive. And we've built our own embedded DSL in Lean, where we can use basically the syntax that we're all familiar with. We painstakingly went through the grammar that MLIR has, in this case, the generic syntax, and we've translated that into Lean's mechanisms for extensible syntax. And then we've gone even the extra mile and added like pretty versions of the DSLs to even get those versions of the syntax. So we define the left-hand side, we just say some program that computes x plus 0. And then the thing we want to optimize this to is just x, because adding 0 is nothing. So then to say that this is a people rewrite, well, first we define, okay, this is the pattern we're matching against and what we're rewriting to the left-hand side and the right-hand side. And then we need to produce a proof of correctness. And in LLVM, like the proof of correctness, it basically always looks the same. We first run our automation that eliminates all the SSA boilerplate. And this kind of takes the embedded DSL and it simplifies the sort of the correctness expression into the pure mathematical expression that we want to decide. In this case, that expression is that if we have an integer with 32 bits, then adding 0 to it, well, that does nothing. That just gives the original integer back. And then we have a whole suite of proof hammer style automation tactics, which in this case will completely automatically close the goal. So suppose you want to play along at home. Do you need to have Lean installed and download a library? No, we actually have a website set up where in your browser you can just get a Lean buffer and play with these things. So here is that same example with the actual source code, and we can see that it succeeded because at the right-hand side we get like the beautiful no-goal statement. This playground works, it lives at lean-mlir.grosser.es, or if you have a copy of the slides and you click it, then it will take you to exactly this file. All right, so that's the happy path. If the automation succeeds, then it tells us, I found a proof, and Lean checks for us that the proof is actually correct. But what happens if we made a mistake? Here's the same example that Chit showed you before, where we're trying to optimize division by constant 0 to right shifting by 13, which is of course wrong. Well, in this case, because the widths are concrete, we're just trying to prove this optimization correct for 32 bits. The automation actually uses a similar solver to what Alive does, and it will give us a counterexample. But we can go beyond that. We can actually prove our optimization is correct for arbitrary widths. So in this case, this is an optimization that we've extracted from Alive, but we've generalized it. We've actually said this is not an optimization that works at some specific width. We're trying to prove it correct for all possible widths. So suppose you have some unusual architecture where you have 512 bits integers. Well, if you rely on the solver, that's going to be difficult. But in this case, well, we've proven it for all of them, so in particular for 512. Again, here's a link to this exact file at the playground. So like I said, we've gone through a lot of test cases. We've formalized a bunch of things from Hacker's Delight. We've formalized a bunch of Alive test cases, and we've also gone through LLVM's Inscombine test suite. And we've extracted a lot of optimizations from there, and we can see that Beefy Decide, that's kind of the concrete width automation, can decide a relatively good bunch of them. But Alive Auto, which is kind of a combination of different tactics we have that for our generic widths, it is actually very competitive. And with special thanks to Lina Farrow and to the MathLab community, and particularly Henrik and Kim, for building a lot of this automation that we can then reuse for our purposes. All right, so that's LLVM. That's the case where we can rely on automation. So what about polynomial? Well, Lean is a particularly good system to work in for us because it has mathlib. And mathlib is the world's largest formal math repo, where a huge community of mathematicians are trying to formalize at least all of undergrad mathematics and beyond that even. And it has exactly sort of the complicated mathematical objects that we need to formalize the semantics of the polynomial dialect. And given the semantics, we can build a proof. Like, this is not as automated. It requires more effort, but it is possible for us to prove things about it. Therefore, we get this nice green rectangle where easy things are easy and hard things are still possible. So how does this all work? Did we just take these two dialects and formalize them? No, we actually build a whole framework where we have the core kind of syntactic data structures that MLIR has, and we give you methods to kind of instantiate that for a concrete dialect. So what is a dialect made of? Well, we say it has two main concepts, and that is we have a universe of types, and we have the operations in the dialect. So in this case, this is a simple example where we say, okay, the only type we have is int, and then we need to give the semantics for this type. And the way we do that is that we kind of give a function that transforms our type universe into a Lean type. In this case, we're saying an integer is just a bit vector of length 32. Then we need to define the operations. Here we have addition, and we have constants, where the constants kind of additionally take a value. Then we need to say what is kind of the type of an operation. So a constant, it doesn't take any arguments, and it returns an integer. Whereas addition, it does take arguments. It takes two integers, and it again gives us an integer as output. And then, given the signature, we need to give the semantics of our operations, again, as Lean functions that kind of have this signature. And there's a lot of dependently typed machinery going on there, which we won't go into. But in this case, we're saying, well, a constant really is just the bit vector that has that value that we set. And addition, well, addition just is a function from two bit vectors, and it gives their sum. So given all of these sort of semantics that we define, then the framework will take in this high-level DSL that we've specified, and it will translate like the const operation into the semantics that we gave for const, and it will translate addition into the semantics we gave for addition. And that brings it all together and allows us to have these nice syntactic objects to play with and still get formal proofs in Lean. But of course, the core problem is we need to know what the semantics of a dialect is. So if you want to have a formal semantics for your dialect, please come chat with us and tell us what it is so we can formalize it. And that is kind of what we have. We're trying to evolve the semantics with MLIR. We're trying to make easy things easy, and we're trying to make complicated things still possible. And we're trying to formalize Peephole optimizations. Thank you very much.
Any questions?
Hi, nice talk. Out of curiosity, in the existing MLIR dialects, have you found something that made your job harder or something that made your job easier? And do you have any advice for dialect designers that could make their dialects easier to verify?
We've not found anything that makes it easier.
Fair enough.
So, I mean, I think generally there's a lot of, at least when I was thinking about this, there's a bunch that's unclear about parallelism and asynchronicity and whatnot, right? Like, it's just super unclear what it means in many of these cases. So that leads to some problems. Also, last year, I think Jeff New and I had a talk about dominance and how it's not really clear what some of the dominance traits mean. So those are sort of the major, like, I don't know, things that at least I've encountered. Alex, do you have other pieces of the MLIR semantics that were unclear? Yeah.
I'll say just in general, documentation. If you have strong documentations for what your intended semantics are, then we can try to formalize them and, I don't know, maybe get back to you and say, like, what do you mean here exactly? And try to go from there. But if there's no documentation for us to begin with, it becomes very hard for us to try to guess what the meaning should be.
Yeah.
Thanks.
Hi, yeah, thank you. Do you have any example of dialect that you cannot formalize? Like it has, like just impossible?
Yeah, very fair question. So Right. So in some sense, we assume that regions behave in a particular way, where more or less we assume that when you have an operation that takes a region, then the region can be sort of treated as a black box function, right? So if you think of a dialect like quant, where the semantics is, like if you, this used to exist, I think it's removed now, but there was an operation called quantize that said that any operations inside the body of this region will now become quantized, right? So that makes it anti-modular, because the semantics of the operation inside sort of the region depends on a parent that could be arbitrarily above. So things like that don't work, but it's kind of like, as long as the semantics is compositional, then we're able to represent it more or less, yeah. There's another fairly big open question around how we do side effects. So we have, so it's like, so more or less it's kind of like this. It's like in the framework, we have support for side effects, but it's really not clear how to build proof automation to reason about some of the really complicated kinds of side effects that MLIR possesses, is sort of the story so far, yeah.
Thank you.
Yeah.
It's pretty cool. I'm curious how big of a scope of things you've tried to prove. It looks like the examples you've shown are sort of a basic block. Have you looked at bigger things, and how big?
Yes. So maybe Alex has it. Okay. So yeah. I mean, we've been sort of currently focused on mostly like the basic block level type of things, right? Because because at least. So like those are the Peephole rewrites that exist that are most pervasive within MLIR.
Mm-hmm.
So for example, so like we do have a couple of rewrites about things like for loops and if conditions and whatnot, right? Like folding them and peeling a loop iteration and things like this. But more or less, I think, like it's not, if you have large scale examples of Peephole rewrites that involve like complicated region related transformations, I would really like to take a look.
I mean, I guess inlining might be the first step in
I guess that's fair, but yeah, I would like to discuss this offline, but yeah, I think somehow like, that's slightly beyond what I would consider a Peephole rewrite. It's more like a inter-procedural transformation almost, right? Yeah. So.
And then it seems like your approach has been to sort of extract some little bits of MLIR and build a model of them in Lean. Have you thought about how to maybe close the gap a little bit so that maybe what you're verifying is a transform dialect kind of thing? Like if I add the semantics and then I say, oh, by the way, here's my transform dialect thing in the transform dialect. Mm-hmm. That's what I want to verify. Or?
That's right.
I mean, that's not a theoretical problem as much as a practical like software engineering.
Yeah, of course. But yeah, I mean, I do think that's interesting. So maybe one of the things that we didn't touch on is that like, so for example, with our like semantics for like LLVM and arithmetic, we do have executable semantics. So we do execute programs and compare it against what LLVM produces, right? So we use the fact that it is executable, at least in that case. And yeah, I think, yeah, using transform to actually, yeah, I think that makes a lot of sense. We should do that, yeah.
Thanks.
Yeah.
Also to add to that, there are some other things that we verify as well. For example, we have a completely verified dead code elimination and common sub-expression elimination. And we are working on some projects where we might look into like verified lowerings between different dialects, but that's still very much work in progress.
Mm-hmm.
Hi, I'm Yu from University of Utah. Thanks for the presentation first. So I have a small question about the verify about the operations. For example, add is easy because it receives 2 integers and returns another integers. But about the truncate, it receives an integer, returns another integer, but with less bit width. So in other words, you have to verify the result in every bit width less than the operand. So can you verify that?
Yeah, so we can, right, so, okay, yeah. So the short answer is yes, we can, but the encoding of the type becomes more complicated, right? It's like the type is no longer like a bit vector of fixed width, but the width can now vary depending on like the instruction that you invoke. So yes, we can encode that, but that just makes things more complicated is essentially the answer, yeah.
And with that, let's thank the speakers.